All right, so we're going to go ahead and work a little bit more with our vectors. And we're going to talk about unit vectors, which are a special kind of vector. A unit vector has a magnitude of 1, meaning no matter what happens, no matter which direction it is, it would be on our unit circle. That is not the pen I meant. So if we had a vector on the unit circle, initial position here, terminal point here, its magnitude is 1. The distance that it's covering is 1. So our vectors that would hit the unit circle with that magnitude of 1 are called unit vectors. That's why it's on the unit circle. So a unit vector has a magnitude of 1. No matter what direction it's pointing, it's a magnitude of 1. So if we went and found the magnitude of 4/5 and 3/5 as the vector, magnitude, that's when we do that distance formula thing. So if we were to find the magnitude of this vector, and we did our square root of 4/5 squared plus our 3/5 squared, we'd get our magnitude of 1. Not equals 1. Okay, so our magnitude is 1. That's the distance it's covering. We're going to have 2 very special unit vectors that we're going to use for a lot of things today, and we're going to call them I, not imaginary I, just I. And that's the vector 1, 0, meaning this guy here. That's I. And J, which is 0, 1, which would be this guy here. I'll show you what we're going to do with those in a minute. But I and J are unit vectors that are on our coordinate axes. So what we're going to do is we are going to find our component form for this set of points we have here. And then we're going to write our component form in kind of a weird way. I'll show you what I mean in a second. Okay, so let's start with finding the component form for this set of points here for our vector that goes from A to B. So just like we did yesterday. That's when we're needing our change in our x's and our change in our y's so we can put it in its component form. So what is the change in our x's? 2 minus negative 6. And our change in our y's, that's our 5 minus 0. So we're looking for the difference in the pieces. So the change in our x's is going to be 8, and the change in our y's is 5. So the component form, I'm going to put it up over here, is 8, 5. Right? That's what we did yesterday. We did those a bunch yesterday. So when it asks us to write these as a product of unit vectors, what that's saying is if I look at I and J up there, I deals with only the x value, right? I only has x's. So if I wanted to recreate this vector at 8, 5, I'm going to sketch it out real quick. So if we had our vector 8, 5 up here, it's going this way. And I wanted to build it out of 1, 2, 3, 4, 5, blah, blah, blah. This would be our i's, goes to the right, and our j's that go up, combining them together, right? See what I'm doing? We would need 8 sets of I, and we would need 5 sets of j's. So 5 j's. So when it says write this as a linear combination, that means if I had 8 i's and 5 j's, and we added those together, we would get to exactly that same terminal point if I just did it in steps. It's like putting it in terms of steps. So when we're writing these as linear combinations of products of the unit vectors, because complicated titles, that's how we're doing this. We're going to practice this several times, but that's what we're looking at to start today. So this one, this one. These are the two I have for you right now. Okay, questions on this first one? We're going to practice it again, because I know it's a little weird. So I've still got our special unit vectors up here, our I and our j. We're going to find our component form and write it as a linear combination of our unit vectors. So start with finding our component form. Find our change in our x's and our change in our y's. What are we going to get for the change in our x's? Okay. Negative 12. Negative 8 minus 4. Sorry, I had to change out the tip on my stylus because it's broken. Oh, and that one's not fitting. Don't you fit? There we go. So this is when we'd have our negative 8 minus 4, which is going to give us negative 12 for our change in the x's. Our change in the y's, yes, going to be negative 4. We have our negative 5 minus negative 1, negative 4. So our component form is our negative 12, negative 4. To write it as the product of our unit vectors, I deals with just x's because there's 0 y's there. If I took 12 letter i's, or negative 12 letter i's, we walk the wrong way. And for our minus 4, we need negative 4 sets of j. So to write this as our product of the unit vectors, we'd have our minus 12i minus 4j. If you just want to put it as a plus and keep the double negative sign here, I'm totally fine with that. But technically, that's a better answer. It's not I the imaginary. It's just I the unit vector. We're not going to have imaginaries in vectors because vectors are all about the real world, and imaginaries are not real. So the fact that they use I here is really annoying, but that's one of those things that vectors do because vectors are weird. So it's not I imaginary, it's I the unit vector, because yay! I love when letters mean the same thing. That's, yep, yeah. It's seriously just taking the x's and putting them with an I and the y putting it with a j. It's like it looks super complicated and it sounds really, really weird. Then the linear combination of the product of the unit vectors. Gross, but it just means what's your x and what's your y. X gets an I, y gets a j. Ta-da! We're done. Okay? So writing them as the product of our unit, or as our linear combination of the unit vectors. Looks gross, sounds gross. Isn't that awful? But we're not going to just live in this land of writing things as our special unit vectors all day today. We've got other things we need to look at because we're going to start looking at operations on our vectors. Yay! So now we're going to look at two different kinds of vectors. So if we have two vectors here. So remember, we can write our vectors with one letter and a little arrow on top. So this would be vector A. And it just has two pieces like normal with our change in our x's and our change in our y's. Just since we're looking at combining two of them, we've just put them as A1 and A2. And vector B is an entirely separate vector. So again, it has an x and it has an y, but since we're comparing the two, we have to put it as B1 and B2. So here our scalars are going to come back into play in our stories here. If we have a number, a scalar, multiplied against a vector, this A should have a little arrow on it. So if we're multiplying 5 times vector A, what that means, it's very much like distribution. Our x gets multiplied by 5 and our y gets multiplied by 5. Because what this is doing is here we go. If we have a vector like this, let's say this is A, and I want 5 A's, it's just 2, 3, 4, 5. So whatever the x value is of A is going to be times 5, and whatever the y value is times 5. So our 5A would be this vector here, 5A. And vector addition and subtraction, if I'm taking, again, these should have little arrows over them. I don't know why the arrows didn't come in. Vector A plus vector B, or vector A minus vector B. We take the x values and add them together, and we take the y values and we add them together, or subtract them, depending on our operation. Because if we are adding or subtracting vectors, what this is doing is if we have, again, I'm going to say vector A here, and let's go with vector B over here. So I'm just going to say, for example, A here, B here. If I want to add them together, we're going to have our A, I'll just make A plus B. It combines them together. Sorry, I'm just making my pen look a little different so we can see it better. A plus B. It combines them together. So we'll take our x's and add them together. We'll take our y's and add them together. If we're subtracting them, same difference. Okay, so we're going to look at that. One thing that's important to notice when we're looking at our vector operations here is we're always looking at this component form every single time. So it's got to be in our component form to be able to do this. So I'm going to give us 3 vectors up here, and we're going to do several operations. So we've got vector W. That is the component form of -4, 1. And again, these should all have the little arrow at the top, but my formatting stuff went a little wonky. Our operations aren't always going to have the arrow over them, but I'm going to put them on here. There we go. So we got vector y that has the component form of 2, 5, and we've got vector z that has the component form of -3, 0. We are going to do these operations, and we're then going to write it as a combination of the unit vectors. So we're going to practice that first thing we did too. So we're going to start by looking at this 4w plus z. So the first thing I'm going to say is we're going to look at 4 times vector w. I am going to chew on that one all day long. I don't know why. So if we have 4 times vector w, well, w is the -4, 1, right? And our scalar multiplication, that's what this is, means we're going to take this 4 times both pieces. It feels just like distribution. So 4w is the exact same thing as if we have -16, 4. mouse. Then we need to include our plus z, which you don't have in here yet, minus 3. Okay, so this is just the 4w over here. Then we're going to do our plus z, which means I'm going to take the x pieces and add them together. So my negative 16 plus negative 3. And we're going to take our y pieces and add them together. 4 plus 0. So what is our combined vector here? Negative 19. 4. What's up? No. We had one yesterday. We're not doing one tomorrow. That would be cruel. Holy cow. I think I would riot too. Just saying. All right. Questions on that bit? So then let's write this as our combination of the unit vectors. So we need our negative 19 that goes with the I, and the 4 goes with the J. It's those same unit vectors we used on the previous page. Uh-huh. I was gonna say, like, the operations? No, this is how they go. Okay. I know.
It's too simple for it to be.
I know we're suspicious. It's okay. It's okay. It's okay to have faith and believe in it. All right, let's look at the middle one. Negative 3 times vector w. So negative 3 times our vector w, that's our negative 4, 1. What are we going to get for negative 3 times w? Positive 12 and negative 3. So as a combination of our unit vectors, 12i minus 3j. Okay. So the third one has a lot of pieces. We can do this. Let's start by looking at 2 times vector w. What are we going to get for 2 times vector w? Negative 8, 2. What are we going to get for our 4y? 8, 20. And then we're subtracting our z, which isn't having any transformation on it, our minus 3, 0. So when we're doing these combinations, you can do it either in a couple of goes, or we can kind of combine things together in one set, where I know we're going to take our x's, we're going to take our minus 8, we're adding the 8, and then we're subtracting the negative 3, because we use these same operations. As I say, or you can do it in a couple of steps. So this is our x's. Our negative 8 and our positive 8 cancel out. We're left with minus negative 3, which is a positive 3. The y pieces, we're going to have our 2 plus the 20 minus 0. That's 22. Because it was the y piece plus this y piece minus this y piece. So our component form of our combined vector here is our 3, 22. So what is it as a combination of our linear vector, or of our unit vectors? 3i and 22j. Okay. Questions on our operation stuff? Awesome. Thank you. All right. So the other reason we have these in this kind of part of the book and part of the chapter is we have times when we're going to use trig functions with these. So sometimes we will be given different pieces of information than the starting point and the terminal point. If we are given magnitude and direction, so we know our angle, we know our magnitude, we can figure out the terminal point. That is our component form. So our x values are going to come from our magnitude times the cosine of the angle, and our y values are going to come from the magnitude times sine of that angle. I was going to say that the operations are not brutal. These do get a little bit gross eventually. Okay. So the whole point of this is so that we could find our point. So we could figure out where this vector is. We know it's got a magnitude of 6 and its angle is 53 degrees. So we can find the x value, this change in x, by taking our magnitude. Our magnitude is 6 times cosine of our angle. So this is going to tell us that delta x, that x value in our unit or in our vector. So 6 times the cosine of 53. Which we are honestly most times going to leave as 6 times cosine of 53. Because it's a super gross decimal. If we type that into the calculator, 6 times cosine of 53, making sure we're in degree form, we get 3.610890139, blah, 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 right? So it's a super gross, it's a non-terminating, non-repeating decimal. We're going to leave this pretty much as our 6 times cosine of 53. If we need to have an actual number there, we can type it in the calculator. But for the most part, we're going to leave it as the most accurate version, which is 6 cosine of 53. So for our delta y, same kind of vibe, giving us our A2, that's going to come from the sine. So this is going to be our magnitude, which we said was 6 times sine of that angle, 53. So our vector, the way we would write this, is going to look like something super gross. Our 6 cosine 53, comma, 6 sine of 53. It's the same pieces, just one's cosine, one's sine. Just like with our unit circle, cosine is the x, sine is the y.
We're gonna have to like add things like that and say we're gonna
Eventually, yes. But we're going to be able to use calculators for it, for sure, especially if we need decimally answers. Okay, same kind of vibe for the bottom one. Trying to write it as a vector if we know the magnitude is 13 and the angle is 47 degrees. We're going to wind up with our change in x's. That's where we get our magnitude times the cosine, and our y's are going to be the magnitude times the sine. So our vector, given this piece of information, we're going to have our magnitude, which is 13. Our x's come from the cosine of our 47 degrees. Our y's are going to be our 13 times the sine of 47 degrees. So it's our magnitude times the trig function of the angle. And again, we're going to write them like that so that we can get the most accurate answers as needed if it comes time that we need to do operations with those lovely pieces, which will happen. Okay. Okay, questions on these two? Because I'm going to give us a time when we're going to see this. They're going to look weird. I promise we'll get through it. Deep breath.
Why is there so many columns?
Because they're trying to make it contextually make sense.
No, I want to see the numbers. Give the formula.
All right. Here we've got that Taylor is walking 45 degrees north of true west for 1,000 feet, and then goes 200 feet due north to the park. We want to know how far she is and what angle she is from her house. So first things first, let's figure out what the heck this thing looks like. So I'm going to say that this point down here at the bottom, this is going to be her house. Ooh, fancy. Wait, I'll give her a floor. Ah, there we go. House. So if she walks 1,000 feet, 45 degrees north of true west. Ugh, gross. So we have north over here. So remember, we never eat those soggy waffles. What quadrant is it going to feel like for 45 degrees north of true west? Careful. Where is that going to be? Yeah. This guy. This is a 45 degrees north of true west. So here is our first piece. And she goes for 1,000 feet. 1,000 feet. Just means west. Straight west. Then she's going to go for 200 feet due north. So from here, she goes straight north for 200 feet. We want to know. Ooh, I'm so good at straight lines.
Yeah.
See if I can do it slightly better, but I don't know if I can. We have some information about our angles, right? This is the guy we want to know.
Isn't the other 45? It's like going straight north. So wouldn't that mean? Just do the coast formula and call it a day.
But let's practice it with our vectors.
I want to do the difficulty of bringing the coast formula.
Then you're going to be doing all kinds of things to try and figure out the correct angles, though. Like, you would need to do a couple of different ways of getting, like, bearings and distance and stuff. All right. So we're going to think of these as two different vectors. I've got my green vector and my blue vector here. For our vectors, especially for this green one, our angle is not based off of west. So 45 is not our angle for that green vector. What is the angle for our green vector here? It's based off of our starting position like we do for the unit circle. So what is our angle for here?
What
180 minus 45, which is
139.
135. Angles are set up off of our x-axis, the positive x-axis, just like for the unit circle. So our angle for this green vector is 135. Because we know it's 45 degrees north of this piece, and this is always our initial point for our angles, because it wasn't given to us as a bearing. It's off of our east, like that where east would be. So we can write the basically address of this point using the magnitude, which is our distance covered, and the angle, 135. So the address of that green point, we could write there as our 1,000. X is coming from our cosine of 135. And the x piece there is our 1,000 sine of 135. And we want to combine it together with our blue vector to get up to where the purple one would be. So we're going to add the blue vector. What is our blue vector going to be? We rebase. I was going to say, what's the angle on it? 90. So our magnitude is 90. Or sorry, no, our magnitude is 200. Our angle is 90. 200 cosine of 90 and 200 sine of 90. It would, true west would be straight up west. Like she goes west, no deviation, west. But she went 45 degrees north of west because she was obnoxious in the way she wrote down her directions. So she pointed her compass at west, which is that way. So west is that way, real life, west is that way. And she went, I'm gonna go that way. So we want to combine those two pieces together. What's up? Because what is the angle for true north? What angle to go north is this guy? That would be south. It's based off of our starting position here. This is our angle for our blue vector because we're headed straight up north. We start from its initial position because we can only add them together in their component form, so it has to be based off of its component form, which would be with the 90 degrees. Okay. Awesome sauce. I'll get those in. All right. Let's add these together. Are there any values in here that we know off the top of our head that are not super awful? Sine of 90 and cosine of 90. What is cosine of 90? 0. And this one is 1. So when we do our addition and we add together those x's, so the change in our x's, we're going to get with our 1,000 cosine of 135 plus our 200 times cosine of 90, which is 0. The change in our y's, so when we combine these together, we're going to get from our 1,000 sine of 135 plus our 200 times sine of 90, which is 200 times 1. So when we combine these together into our component form here, We can simplify this guy a little bit because 200 times 0 is 0. So it's just going to be that 1,000 cosine of 135. And our y's, it's going to be a little bit of a mess, but we have our 1,000 sine of 135 plus 200 times 1, which is 200. That gives us that point for D. This tells us where this guy is relative to the house, to the origin. So this is our component form of going directly from the house to this point. We're asked to figure out how far she went, which means I want the magnitude of that. So I'm going to give us a little bit more space at the bottom. It's going to make the page jump kind of weird. I'm going to fix it. There we go. So if we want to know the distance she goes, we want to find that distance that I marked out as D. That is the same thing as the magnitude of that vector that I put the star on. So we want to find the magnitude of this guy. That tells us the distance. So our magnitude, that's when we do our square root of those things squared. Ew. Calculators. We love them. Oh, sorry. I got to not zoom that in. I have to zoom significantly less than normal because you guys are linked to me. So we're going to take our 1,000 cosine of 135 squared plus, make sure you use your parentheses because we have our 1,000 sine of 135 plus 200 squared. We're going to type this whole thing into the calculator. You can do it all in one go. You can do it in a couple of bits, but we're going to get to the whole thing to figure out this distance. So type the whole thing in. What do we get? More than 1. Like you for real got 1. Let me see your calculator. But I'm pretty sure that was just a chaos pop-up. Yep, 1,150.15 based on where we round. Feet. So she is 1,100.15 feet from her house right now. That's the distance. That is distance D. To find the angle, we want to know this angle. That's when we are going to use our theta equals our inverse tangent, arctangent of y over x. So it's using our stuff from yesterday in these super gross vectors. So they get gross. The calculations themselves are not hard, but the vectors look super gross. Okay. So we're going to do our arctangent of our y, which is our 1,000 sine of 135 degrees plus 200 over our 1,000 cosine of 135. It's a lot of stuff. Aren't we glad we get to use calculators? Okay. So we type that in the calculator. It's going to spit out negative 52.1 degrees. Is that the right angle for us?
Yes.
What quadrant is that in?
Negative. Or 4.
I was gonna say, I have heard all 4 different quadrants.
4.
4, that's in quadrant 4. So what do we do to get it to be in quadrant 2 where we want it to be? Add 180. So our angle is really 127.9.
Wait, why?
Because minus 52 is down here.
How do we know it's quadrant?
Oh.
Because we always start off of this right-hand piece. Say it again.
How do we know it's quadrant 4 and not quadrant 2?
Because when we take inverse tangent, it comes off of the angle 0. It's based off of a 0 from a unit circle. Think on the unit circle where angle 0 is.
Oh, and we can only be on the...
So that's going to go down this way from angle 0. Okay? So the stories look gross, but we can do them. We can. We don't want to, but we can.